Sorry about that.
Oh, you're okay.
So if we're talking about an Arrhenius acid, we're gonna, so it's a substance in water that produces H plus or H3O plus. Okay, so this means that it has to be in water. And it has to produce a proton when interacting with water. Okay. We're talking about an Arrhenius base. Right, this is something that produces hydroxide ions in water. Okay. So it has to produce a hydroxide ion in water. So an Arrhenius acid, usually it's going to do AA. It's going to be some HA substance. So we throw in water to produce H3O plus and A minus. An Arrhenius base, you can either have a BOH that just breaks down into B plus ions and hydroxide ions, or we can have a base that reacts with water. This will always be a equilibrium that produces BH plus OH minus. Okay. With Bronsted-Lowry acid, here we were talking about a substance that donates a proton. So here we don't need water. Right? But we do need a substance that has a hydrogen to have an acidic hydrogen. Okay. By the way, I forgot to mention this earlier. An Arrhenius base, it has to be in water. Most bases are going to be able to be described by Arrhenius as long as they're in water, but the acids are a little bit more restrictive for your Arrhenius. With our Bronsted-Lowry acid, again, we have to have something with a hydrogen or a proton, acidic hydrogen. So that's kind of the real restriction with that one. But it'll look the same way as our so HA going to H plus A minus, or HA plus H2O going to H3O plus A minus, or we can even do HA plus B going to BH plus A minus. Or, HA plus BOH going to BH wait 1 second. That was wrong. Going to BA plus H2O. This is a classic neutralization reaction. So we're donating our proton in each one of these, right? So they're going either just free, or they're going to the water, or they're going to the base, or they're going to go produce water. And then generally in this form, these will actually combine to give us BHA or something like that. Really, we'd write it HBA, but something like that. Okay. Our Bronsted-Lowry base. This is a substance that accepts a proton. So this one is, again, a little bit, I mean, they're all going to have their drawbacks. This one, you have to react, or you have to, all right, sorry. This is only a base when reacting with a Bronsted-Lowry acid. So you have to have something that's defined as a Bronsted-Lowry acid in order for this to be a Bronsted-Lowry base. Okay. Which does limit it a little bit. And the reason I say this is if we just write BOH and it is in water, it's not accepting a proton in this case, right? So it's not, we don't really consider this to be, so not a Bronsted-Lowry base in this case, right? Which can limit that. But if we have just B plus water, we would produce BH plus and OH minus. So it has accepted a proton, so this would be a Bronsted-Lowry base. And then if we take it and we react it with an acid, this would also be considered a Bronson-Lowry base. And again, this is our neutralization.
Why would that one be a Bronson-Lowry base?
Because it is accepting the hydroxide portion of this is our base, and it's accepting a proton.
Okay. In the top one, so the reason it's not a Bronson-Lowry base is because,
There's no proton.
okay,
If this hydroxide then went and reacted and got a proton to produce water, then it would be considered a Bronson-Lowry base. But just throwing a base in water, we don't look at it as a base in that manner. Granted, throwing a base in water, that's not really, you're not having a reaction occur, you're just having a dissociation like you have when you throw an acid into water. With an acid in water, you dissociate, and then that hydrogen goes and attaches onto the water. Okay. Other questions that you had about any of that stuff that we went over on Thursday?
When you were checking to see if it would be like a strong or weak acid or base, how would you be able to, how do you know?
So we're gonna technically go over that on next Tuesday, but I can go ahead and start you up on that. So for acids, they are only strong if they are included in this list. H2SO4, the first proton. HNO3. Sorry, having brain fart. HClO4. HClO3. HCl. HBr. HI. So there are 7 strong acids, and you guys will be required to memorize those. Sorry. Trying to figure out. Okay. Bases. These are either going to be hydroxide containing, so alkali and alkaline earth metal hydroxide specifically are the ones that are considered strong bases. So alkali, we're talking about like sodium hydroxide or potassium hydroxide. alkaline earth, we're talking about stuff like calcium hydroxide, and there are some that are not included in that list technically, but it's fine if you just remember that it's the alkaline earth hydroxides and the alkali hydroxides.
Okay. And then the conjugate bases and acids.
Mhm.
I was confused on those.
Okay. Sorry, just gonna keep messing with it. So the conjugate acids and bases are, we're talking about a conjugate acid that is the base plus an H plus. Okay, so if NH3 is our acid, sorry, if NH3 is our base, NH4 plus is our acid, or conjugate acid.
Will we have to be able to tell if it's an acid or a base, or will we
Yes.
be spotted?
You need to know if it's an acid or a base. Generally, your acids are going to be in the form of HA. So the hydrogen will be written first.
Okay.
If you do not see the hydrogen written first, it is highly unlikely to be an acid.
Okay.
I can't think of any acids off the top of my head where the hydrogen's not written first. Oh, I lied. CH3COOH. That is an acid where the hydrogen is not written first. This is acetic acid. Any organic acids? Yeah, I guess I should have. Organic acids. Organic acids are going to have a COOH on them. So it's going to be some substance and then COOH. So we have stuff like benzoic acid, C6H5, COOH, acetic acid, CH3COOH, ethanoic acid, CH3CH, or sorry, propanoic acid, what am I saying? So yeah, if you see that COOH, that is an organic acid, and this H next to the oxygen is the one that is acidic. So that'll be the one that'll be removed. But besides that, the rest will be H. For your bases, they're going to be so we have amine bases. So that's a nitrogen containing base. So it has a nitrogen with a pair of electrons. And then some other stuff on it. It could be NH3, NH2, CH3, N, CH3, 3. So as long as you have a nitrogen with a pair of electrons, and each of these have a pair of electrons, it's considered a amine base. You have hydroxide bases, which are the easiest ones to recognize. So that's going to be some BOH compound. So you'll see that hydroxide in there. That does not include water, even though some people think it does. That is not a hydroxide base. Or yeah, that's not a hydroxide base. You also have sulfide bases. So that's going to be a S with a pair of electrons. Or technically, I guess I should write, it's an S2 minus anion. So you can have something like Na2S, and that would be considered a sulfide base, CaS, a sulfide base, stuff like that. And then the S itself, it does have the pair of electrons, and that's how it can take that hydrogen. And then you also have carbonate bases. So carbonate base, or a bicarbonate base, both of these are considered bases. It's going to have CO3 2 minus or HCO3 minus plus an cation. So something like calcium carbonate would be a base, something like sodium bicarbonate would be a base. As a note though, H2CO3, this is an acid. This is carbonic acid. This is calcium carbonate. This is sodium bicarbonate, or sodium hydrogen carbonate. Okay. So you do need to, and I'm glad this is all going to be in the review because you guys need to know your acids and your bases. You should also be able to write a acid-base reaction, right? So the types of acid-base reactions are going to be based on the base itself. So if you have a hydroxide base, plus acid, the hydroxide base is considered a strong base. So when it reacts, it'll react completely. So this is a complete reaction, meaning we're going to have a one-way arrow. Okay, so it's going to be a BOH plus HA goes to Ba plus H2O. The net ionic for this is OH minus plus H plus goes to H2O. Okay. Hydroxide base is super easy. You just need to make sure that you balance out. For every one hydroxide, you have one proton. If you have two hydroxides, you're gonna need two protons. Three hydroxides, three protons, so on and so forth. With our sorry, yeah, that's right. With our amine bases, plus an acid. An amine base is a weak base. So if we have a weak base plus a weak acid, that's going to be equilibrium. If we have a weak base plus a strong acid, that will be a one-way arrow. Okay. So I'm just gonna do actual examples with these. So if we have NH3 plus CH3COOH. So we have the weak base ammonia, the weak acid acetic acid. You are going to form two salts, NH4 plus and CH3COO minus. But those are going to combine to give you NH4 CH3COO.
So this is a weak base and a weak acid.
Correct.
Then why would the arrow not be equilibrium?
Oh, I'm sorry. Yes,
Okay.
that is supposed to be an equilibrium arrow. My bad.
Okay.
I was even trying to like point that out. And then I missed it. Okay. Now we have a weak base, ammonia, plus a strong acid, hydrochloric acid. That will not be, that will go completely. So again, we're going to produce those two ions, but they will go to form NH4Cl. So with these, you have N, and I'm just going to put R plus HA. All right, so this R is anything that's attached to that nitrogen. As long as you've got that pair of electrons, it doesn't matter what it is. What you're going to produce is NHRA. The hydrogen will go over to the nitrogen, and then you'll have the rest of the complex. So this is a cation and an anion to produce one salt. So while with hydroxide bases, when you react them, they produce a salt and water. With amine bases, you're going to produce just a salt during their reactions. So hydroxide produces salt and water. With amine bases, you just produce a salt. Okay. I don't really do much with sulfide bases, but I will go over one example. So let's just do calcium sulfide plus hydrochloric acid will produce H2S plus CaCl2. Like so. So here we produce, instead of water, we produce hydrogen sulfide. Which is a very, very weak acid. And then a neutral salt.
And what type of reaction was that?
This is a sulfide base, sorry. Okay. Now let's look at a carbonate base. So carbonate base, this one's a little more common. So we're going to have some anion, or sorry, cation, with our carbonate. Plus, oh, as a note, carbonate is a weak base. Sulfide is also a weak base. So if we have a weak base plus a strong acid, it's a one-way arrow. If we have our sulfide base, so if we did CaS plus one second. I'll check something real quick. Yeah. Sulfide base plus a weak acid, this would be an equilibrium process. Oh, ha. Sorry.
No, you're good.
Look up like, oh my god, it's frozen. Oh wait, no. I see. Okay, carbonate base. Weak base. If we react it with a strong acid, keep in mind that'll be a one-way arrow. Our carbonate base plus a weak acid, we would have an equilibrium arrow. So reacting this with nitric acid, for instance, we're going to produce, in this case, carbon dioxide, water, and a salt. So with the carbonate base, you produce a gas. Oh, by the way, hydrogen sulfide is also a gas. So those are gas forming reactions. Water and a salt. Bicarbonate bases. Same idea, we have a weak base. So if we're reacting with a strong acid, it'll be a one-way arrow, weak acid, and equilibrium arrow. So I'll do both of them with this one. So BHCO3 plus HClO4 goes to water, carbon dioxide, and our salt, BClO4.
How do you know which one will form the salt?
All of them form a salt. Every single one of these will form a salt.
But when you look at your reactants, how do you know which one's gonna go to what? So
Oh, so pretty easy. After you know what to do, let me just get a different color pen. So I can put this out. So your hydrogen, your carbon, and your oxygens will form your carbon dioxide and your water. Okay. Everything that's left over is your salt.
will the carbonate and bicarbonates always produce water and CO2?
Yep, and a salt. So
Okay.
here, oops, wrong color. Here we've got, again, here hydrogen. And our carbon and our oxygen from the carbonate will produce the water. And then what's left over will produce our salt.
Now, if this were to need to be balanced,
Do that.
wouldn't it still balance the same way? Like if it had to be balanced?
So these do have to be balanced, and I did balance these. So with the bicarbonate, sorry, with the carbonate base, this is a 2 minus. So we have a 2 right here. Although we could have also gone for a 2 plus ion here, but we have a 2 here, and then we have a 2 right here. And we'll produce 2 waters and 2 salts.
Gotcha.
If we have a 2 plus ion, it'll be a little bit different. If we have something like calcium. So calcium carbonate plus H Cl goes to CO2 H2O plus CaCl2. But for a bicarbonate base, you only need 1 hydrogen because one of the hydrogens is provided in the base itself for your water. For a carbonate base, you have no hydrogens there, so you need 2 hydrogens. Both of those need to come from your acid. Okay, I have got another class that I have to go to.
Okay.
Were there any other questions that you wanted me to hit real quick before I end this?
No, this covered all of it.
Oh, good. The only thing that I didn't go over that I wanted to was naming of acids and bases.
Mhm.
But I believe I have a review video of that I can put up on D2L.
Okay.
Somewhere. But I hit all of the neutralization reactions and just about all the material went over yesterday. So wonderful. Okay. I hope you have a lovely weekend. If you have any questions as the weekend progresses, let me know. And
Okay.
I'll see you on Tuesday.
Thank you.
Thank you. Bye.
Bye.